In section 3, we're going to talk about capillaries. So these are our smallest and most delicate blood vessels that we have in our circulatory system, but they perform some of its most vital functions. So these vessels are really, really narrow. Only a single erythrocyte can pass through at a time. We talked about previously in the blood chapter how erythrocytes even have a special protein called spectrin that allows it to kind of fold into a taco-like shape because the diameters of some of these are actually even smaller than an erythrocyte itself. So the design of the capillaries is really essential because of its function, which is to allow for gas exchange of oxygen and carbon dioxide, as well as nutrient, metabolic waste, hormones, and other small molecules to be exchanged between the blood and interstitial fluid that's actually bathing the tissue cells. So they don't have the typical three-layered structure of the larger vessels. They have a thin endothelial lining that is specialized for this exchange. All of the endothelial cells are going to be tightly joined by our tight junctions that you learned about in A&P1, but they are interrupted by what we call intercellular clefts. And these are just small gaps that allow for the passage of different fluids and solids. And these clefts are really, really narrow. They're narrow enough to retain most cells and large proteins while still permitting the exchange of essential small molecules. An important and often overlooked component of capillaries is the presence of pericytes. These are spider-like contractile stem cells that wrap around the endothelial cells. And the pericytes not only help stabilize the capillary walls, but they also regulate capillary permeability, meaning what can go pass between the blood and the tissues themselves. And they also play a huge role in vessel repair and regeneration. So emerging research even suggests that these cells may contribute to angiogenesis, which is the process of the formation of new blood vessels, particularly in response to injury or ischemia, making them really important players in both health and disease. So capillaries can be categorized into 3 structural types. We have continuous capillaries, we have fenestrated capillaries, and sinusoid capillaries. So you don't need to know a huge amount about all of these different types of capillaries, just a little bit of information about what distinguishes between the 3. So our continuous capillaries, these are going to be our most common. They're found in areas like our skin, muscles, lungs, and even our central nervous system. And they have uninterrupted endothelial linings and the tightest junctions, really making them ideal for areas where controlled exchange is needed, such as our blood-brain barrier. This is going to feature a lot of almost impermeable continuous capillaries with very limited clefts. The next type is going to be our fenestrated capillaries, which have really large pores, which we refer to as fenestrations. That's where they get their name from, in the endothelial lining that help increase permeability. And these are going to be found in tissues where active absorption and filtration occurs, so places like our kidneys, intestines, and our endocrine glands. And the final type is going to be our sinusoidal capillaries or sinusoids, and these are going to have the most permeable walls, not only with fenestrations, but also with really large clefts, and even discontinuous basement membranes. So these are found in specialized organs like the liver, the spleen, bone marrow, where large molecules, even cells like leukocytes and platelets, can move freely between the blood and the tissues. So these various capillary types, they're organized into capillary beds, which are really just interwoven networks located between our arterioles and our venules. And together, these beds facilitate microcirculation, which is just the process of blood flowing from the arterioles through the capillaries and then into the venules. And this flow is not uniform or constant, but instead is going to be tightly regulated by the diameter of the upstream arterioles and the terminal arteriole that feeds into the bed. So when tissues require more oxygen and nutrients, we're going to send local chemical signals, things like low levels of oxygen or high levels of carbon dioxide, that are going to stimulate vasodilation, helping to increase the blood flow through the bed. The reverse would be true if arterioles constrict to help reduce or even bypass flow. This regulation is going to allow blood to be shunted from inactive tissues and prioritize to the active ones. So, like I mentioned previously, if we are exercising, we would want to shunt the blood to our skeletal muscles and take it away from our digestive organs during digestion. We also have those vasomotor nerve fibers from our autonomic nervous system that can also help adjust the arterial tone based on our physiological needs.